Hello and welcome. This is an overview of solving inequalities algebraically and graphically. Now, if you're looking for the one that says equations, it should be the video before this one. And the equations one is going to highlight some things such as factoring and whatever else. Inequalities will kind of skip, like I'm going to be doing factoring here, but I'm not going to be teaching the factoring so much and not so much rational equations. I'm going to say how inequalities come to effect here. Now, in this lesson, you will learn how to solve linear inequalities, compound inequalities, inequalities involving absolute values, polynomial inequalities, and rational inequalities. And you're also going to deal with some domain restrictions, specifically in the rational inequalities. I'll talk a little bit about square roots as well, not having to do with inequalities, but you'll get a little bit of that as well. Okay, starting with some basic properties of inequalities. First, let me kind of define what an inequality is before we truly start looking at them. To solve an inequality in x means to find all values of x for which the inequality is true. That makes sense, just like equations. When you find a value of x, it means that when you plug it back into there, it's going to make a true statement for your equation. But inequalities are a little bit different, right? The values of x for which the inequality is true are called its solutions, okay, just like equations, and they are said to satisfy the inequality. So if I get a value for x, if I use a value for x that works for my solution, it satisfies it. Makes sense? Inequalities are solved much like equations. So basically, you have a left and right side of the inequality. You're trying to get x by itself, and you do the same thing. You do balance. Whatever you add on one side, you add on the other, stuff like that. And you just try and get x by itself until the variable is all by itself, and then you've solved it. You have a statement there, and we will see what that statement looks like in a bit. So while equations have this whole thing about trying to see how two things are the same, inequalities are a little more about how things are different. So you are comparing two things as opposed to really, I should really say contrasting here. For equations, you're really saying that this is this thing. Inequalities say, well, this is bigger than this thing or smaller than this thing. Sometimes it's equal, but not only equal. So linear equations tend to have just one solution, right? You tend to just say, oh, x equals 2, x equals 7. In a linear equation, sometimes you can have all real numbers and no solutions, or just one. But that's it. Inequalities, you're going to have an infinite set. You're going to have, even if your inequality was only between the numbers 0 and 1, and I know I'm overstepping by starting to write out an inequality before you actually see them, but let's say your statement was this. X can be any number between 0 and 1. You might be thinking, well, that's still a finite amount of numbers. Sort of, but sort of not. Between the numbers 0 and 1 is an infinite set of numbers. You can divide 1 in half, you can divide 1/2 in half, you can divide 1/4 in half, and etc. You can keep going. You're never going to run out of numbers there. So there's an infinite set within there as well. So all we do is we write that inequality simply like that. X is any number between 0 and 1, yada yada. Now, again, I was overstepping, but I was letting you know kind of what it meant. Even within finite space, there's still an infinite set. It does not have to extend infinitely in one way. Here's one property I just want to go ahead and throw out there right now just so you're very well aware, and I'll use numbers to help you out with that as well. We know that 3 is greater than 2. Negative 3 happens to be less than negative 2, however. This is always the case. If A is greater than B, then negative A is less than negative B. The reason why I'm stating that now is because we're talking about solving inequalities, right? And what's going to happen is there are a lot of times where you're going to get a negative x scenario, such as that one right there. And when you want to flip it like this, what happens is the inequality flips as well. This happens when you multiply or divide by a negative number. In this case, if you multiply both sides by -1 or divide both sides by -1, the inequality also flips to satisfy that statement. I want to get that one out of the way as soon as possible because I know it's going to show up a lot later. And this was under properties, of course. Okay, some more properties of inequalities here. Now I'm going to start looking at the visual aspect of it, how they're graphed. Inequalities, at least when solving just for one variable, they're graphed on a number line, on a real number line. When x is greater than a number, or when x is less than a number, you want to indicate all of the values that x could possibly be. Okay, so that's, we're going to graph them there. And I'll explain how that graph kind of works. The value that a variable compares to in an inequality is called the boundary value. So if x was greater than the number 3, 3 is that boundary value. And when you plot that, I'm going to draw a number line for you. When you do that on the number line here, let's say I'm going to include the number 0. Okay, 3 is over here. I'm not going to do all of them. Let's say I'm saying something where x is greater than 3. Okay. 3 is my boundary value, meaning that that's that area where it's not going to cross, or where it begins, actually. It's a sort of threshold, if you will. And what you plot on that is a point. And obviously the point on the boundary value is called the boundary point. So a boundary point is either drawn one of two ways, as an open or a closed circle. An open circle kind of just means hollow, like that. A closed circle would mean it's filled in. An open circle means that it does not contain this actual value. So when I say x is greater than 3, let's start testing some numbers here, for example. Is the number 3 greater than 3? No, because 3 is not a part of this solution set. The number 4 is greater than 3, so 4 is a part of the solution set. I could put a closed circle there. I could put a closed circle at 5 and 6 and 1,000 and all that. However, what we're going to do instead of doing just a bunch of points, we just want to say it extends infinitely. So you can think of what we do when we graph lines on a Cartesian coordinate plane. We are going to draw a dark ray in this case, not a segment. We'll do a segment maybe later. But we're going to draw a ray with a tip here and tail extending out this way. So we're just going to draw a nice arrow that goes in that direction, because this says these are the values for x. Right there. X can be anything greater than 3, even 1,000, and this arrow indicates that. A ray is drawn when the solution set extends infinitely in either direction, in this case in the positive direction. And if you draw a segment, it would be because it's between two numbers. So when I did that statement where I said x is between the numbers 0 and 1, and I'll do including 1 this time. Let's say x is greater than 0 and less than or equal to 1 right here. Here's 1. Okay, I would draw an open circle at 0, a closed circle at 1, and I would draw a segment that goes between 0 and 1, because this says this is all that x can be. It can't be 0, it can be 1, it can be anything in between. Statements kind of like that. So that's the ray versus segment kind of argument, if you will. Some more properties of inequalities, even though I didn't put that. Now let's start talking about what I actually just was talking about. So doing examples before examples, of course. When we compare a variable to a value, I'd say it is advised, but I really advise that you state the variable on the left side of the inequality. So when I said x is greater than 3, I placed x on the left. If I wanted to switch this around, it would have a 3 here. This arrow would go this way. You'll kind of see why when we start talking about this. These both mean the same thing, but here's why we want to do this one. So first of all, here's how variables are read. Greater than, less than, greater than or equal to, less than or equal to. Because we read left to right, we do that thing. X is greater than 3, or saying 3 is less than x. These both mean the same thing. However, when you graph, keep in mind, when we did x is greater than 3, 0, 3, notice when we said x is greater than 3, we drew x to the right of it because we wanted to ensure that all of these values were greater than it. The fact that we use the word greater than makes us start thinking about drawing something to the right. Now when you see something like this where it says 3 is less than x, and I kid you not, a lot of students have done this, and they graph it, what do? They hear less than in their head because less than is the term that was being used, and they go this way. Now the reason they're going this way is because they are hearing less than, even though 3 is comparing to x as opposed to the other way around. Well, this x has numbers that are less than 3. What if I plugged in 0 into here? Is 3 less than 0? Definitely not. So I went the wrong way with that. So it's a lot better if you use it based on what's being stated here from left to right, and you compare the variable to the value as opposed to the value to the variable. If you end up solving for x on this side, just go ahead and flip it so that it's over on that side. I promise you when it comes to graphs, it's really going to help you out. Now there are some here, you see the greater than or equal to, less than or equal to. Again, that means that it also includes the boundary value. The solution set does, that is. Now statements can be represented as a double inequality, also called a compound inequality. I just did this when I was talking about between 0 and 1, right? So basically it's two different inequalities, but they're written as a single statement. Now we only do this if it's between two values and not on the outside of two values. So what this one means right here, -1 x 9 like that, negative 1 is less than x is less than or equal to 9, it means that the value of x is between the numbers negative 1 and 9. Now it includes the number 9, it does not include negative 1. We know what those drawings look like, I just drew one before. So this does mean if you want to write this as two separate inequalities, it would say x is greater than negative 1 and x is less than or equal to 9. Because what if this said or, right? If this said or, you would just have to satisfy one of these two things. If I put the number 11 in for x, is 11 greater than negative 1? Yes. Is 11 less than or equal to 9? No. But if I just need one or the other, then the statement would be true, which means literally, actually, my solution would be all real numbers. So I really need and. Is 11 greater than negative 1? Yes. And is it less than or equal to 9? No. So it would not satisfy that. So anyway, this is the one exception that I would suggest to y'all if to not have the variable placed on the far left. So as you can see, the variable's in the middle. I guess you'll just have to say x is between negative 1 and 9 in this case. But you still have to think of x as being greater than negative 1, not less than it. Okay, so let's do some examples here of solving them, and then I will go ahead and graph them afterwards. So I don't forget, I'm going to go ahead and draw some number lines right there. Perfect. So in order to solve for x here, basically treat it like an equation. In fact, if you would like to, all you have to do is not forget about it later, but if you'd like to, put an equal sign there. If you're bothered by the inequality statement right there, let's just find the boundary value first. And then what we can do after is we can test and figure out where the boundary, what side of the boundary value we should graph on. But notice, as this is less than, this will remain as less than as long as you don't do any random flippings on your own, and as long as you don't multiply or divide by a negative number. Now, I guarantee you that this problem type I gave you might have something very strangely like that. So let's check it out. Let's just go ahead and solve for x. In this first case, I'll go ahead and subtract 7x over to the right side. And I'm going to subtract 8x over to the, 8 over to the left side. So now we are left with, let's see, gone. Now we have negative 10 equals 2x. Divide both sides by 2. You'll get x equals negative 5. Now, of course, negative 5 equals x is read left to right. And here's where, okay, we solved for it. Here's where you can start to bring down your inequality again. If you want to change that and you want to make it say greater than, awesome. Negative 5 is less than x. But what did I suggest? Get your variable on the left side. X is greater than negative 5. Now, let's say we didn't know this yet. Let's say I stuck with x equals negative 5. And I knew the boundary value. Here's how you just got to graph. Give me a 0. Or, give yourself a 0. Give your teacher a 0, whatever. Add a 0. Put where negative 5 is in relation to 0. And state whether or not you're going to go to the right or the left. Now, first of all, this was a less than or greater than. We're still not sure which way it goes, but we know it's not going to be equal to negative 5. So if you test negative 5, this obviously wouldn't work. Now, when I test a value, I have to test it in the original inequality right here, because this is the one that we know we didn't mess up. So here's really what you can do. You don't have to put less than or greater than just yet. Okay? Let's say I did not know that this was my answer. What you can do is you can test another number on the right side or the left side of the inequality, and you can see whether or not you will get a true statement. Now, if I test the number 0, 0 is a very great number to test. The reason is because a lot of your stuff's just going to go away. If I test the number 0 into this inequality, if I get a true statement, that means I should be graphing on this side. If I get a false statement, then I should be graphing on this side. Basically, what we're asking is 0 a part of the solution set? So if the answer is yes, we will graph over there. If it's no, we won't. 7 times 0 minus 2 is less than 9 times 0 plus 8. Notice I'm using the original inequality. I'm using less than to see what would happen. Negative 2 is less than 8. Now, anytime I do test 0 from here on out, I'm not actually going to write any of this. This just goes away, right? It's just negative 2 is less than 8. Is this true? Yes, it is. This is true. Therefore, 0 is a part of your solution set. Therefore, if you did the rest of the math right, anything greater than negative 5 should be a part of the solution set. So once you're at that x equals 5 stage, and you don't know what side to test on, or you're not convinced, I would go ahead and test a value. And I would, honestly, I would test the number 0 all the time. As long as 0 is not your boundary point, 0 is the cleanest number you can test. I guarantee you. So there's your solution. The second way we could have done it, solving this, I could have subtracted 9x to this side and added 2 to this side. And I would have gotten negative 2x is less than positive 10. Now I divide by negative 2, and here's where the inequality should flip. So it says x is greater than negative 5. As you can see, that inequality should flip based on the first property that I gave you guys. Okay, the second one, it's a compound inequality. Now this one, there's not too much to this problem. I didn't really provide a lot. But compound inequality. You have two statements here. 3x is greater than negative 10, and you have the statement 3x is less than or equal to 14. So you really have two of them. You really got to solve both of them here. What some people do is they keep it as a compound inequality, and then they apply whatever things they have to do to x. For instance, divide by 3. This isn't a very long problem. Divide by 3, and they will just do it here. They say divide by 3 on all sides, if you will, and everything should be the same. So as long as you do everything to every quote-unquote side of this inequality, you should be fine. So in this case, it would be x is negative 10 thirds, and x is greater than negative 10 thirds, and x is less than or equal to 14 thirds. And it's good to just rewrite it as a compound inequality again, where the smallest number is on the left, x is in the middle, again reversing this, and the largest number is on the right. And this is what you see right here. You see that compound inequality, boom, there it is, and there's your solution set. And it looks like all is good and gravy there. To graph this, let's get 0 on there. Let's get negative 10 thirds. It's somewhere in the negative direction. I don't know exactly where. I guess a little less than negative 3. And positive 14 thirds, it's pretty close to 5, but right there. Now, if x is greater than this one, but less than or equal to this one, we'll have open and closed circle. We'll get x all inside here. And if you're not sure that your answer was correct, as at least for the where x should go on the inside, on the outside, how should that be? We can test 0 again. And this time if we test 0, we expect a true answer back in the original thing. So is negative 10 less than 3 times 0, which is 0? Yes. Is 0 less than or equal to 14? Yes. So this is true. This checks out. We got it right. Okay, I'm moving straight on out here, solving absolute value inequalities. This is where stuff gets, I'm not going to say trickier, not quite yet, but this is where you really got to know how your absolute value stuff works. So I copied kind of some of this stuff over from the equation video, the definition and what this stuff means and says, all this text here. So absolute value means distance from 0 regardless of direction. Magnitude is all that is important. Absolute value does not necessarily mean make things positive, okay? All we're talking about are two different directions. So as we were looking at before with if a is less than b, then negative a is greater than negative b, stuff like that, that's going to apply here as well. Notice how the inequality flips when your sign changes. Because as you can tell, here's 2, here's 3. 2 is less than 3. But is negative 2 less than negative 3? Absolutely not. So what's going to happen here is when you take the absolute value of a number, you have to remember that it just becomes, it does become the positive version of it as far as comparing values is considered. So if you're looking at the absolute value of x being less than some constant a, let's say that a is 3. And if I want to make sure that my x value is so that when I take the absolute value of it, it's less than 3, well, what numbers can I take the absolute value of that will be less than 3? Obviously not 3. And obviously nothing bigger than it over here. And what's the absolute value of 2? Well, it's 2. Absolute value of 1 is 1, 0, 0. The absolute value of negative 1 is positive 1, right? I should just say 1, but compared to 3, it's less than it. The absolute value of negative 2 is 2. The absolute value of negative 3 is 3. And is the absolute value of negative 3 less than 3? The answer to that is no. This looks to be kind of one of those other endpoints here. I should really be doing open circles right now. Here, let me do that. So when I'm testing 3 and negative 3 against this, it doesn't seem to work. So what's happening is that when I'm taking the absolute value of a number and I want it to be less than, in this example I'm just doing 3, but when I'm taking the absolute value of a number and I want it to be less than something, then that something needs to be between the negative and positive version of that value, just like this one. If the absolute value of x is less than 3, that means that x must be less than 3 and x must be greater than negative 3. It has to be within negative 3 and 3 for this to work. If I do negative 10, yeah, negative 10 is less than 3, but not the absolute value of negative 10. So it's one of those things that when you're less than, you are within. Now, you can think of the opposite of that. What if you are outside of it? We'll keep that there. What if you are outside of it? What if the absolute value of x is greater than a? Well, let's use another example. How about 2? Here's 2. Okay, let's start testing some values here. Let's say, is 3 greater than 2? Yeah. Is 4 greater than 2? Yeah. Oh, awesome. Now we're on the way there. Let's go to the left. Is 1 greater than 2? No. Neither is 0. Neither are any of these. Obviously, none of these are, but we're talking about absolute value. Is the absolute value of negative 1 greater than 2? No, because 1 is still not greater than 2. How about negative 2? No, not even 2. 2 is not greater than 2 either. But the absolute value of negative 3, yes, that is greater than 2 because the absolute value of negative 3 is positive 3. So this would be a part of my solution set. Now, negative 2 seems to be one of those boundary lines again, right? How about the absolute value of negative 4? That's greater than 2, negative 5, negative 6. So what happens here is this splits on the outside. Your x values, this is one of those things. Now, this is not called a compound inequality or a double inequality. These are two separate inequalities separated by a union, by an or right here instead of an and or a within. So now that you write two inequalities, you can't write this one as a compound inequality. You can't say x is greater than a and less than negative a or something like that. That it doesn't quite work that fashion. You are going to separate it with two things. Separated by the word or. That's a big one because you can't be less than 2 and greater than 2 at the same time. You can take the absolute value of it and make it greater than 2. But as far as these statements go, it needs to be separated by an or. But anyway, so those split apart. These stay within. And it has to do with this absolute value stuff here. So I got 4 examples for you. Let's go ahead and do them. Starting with number 1, the absolute value of x plus 11 minus 4 is less than or equal to 0. Okay, the first thing that I did not say for this kind of thing, and this problem's probably harder than number 2, is that you must isolate your absolute value inequality to make any such statement that it is you want to make. That's true for equations as well. You have to isolate it first before you make any claims. So first thing I'm going to do is go ahead and add 4 to both sides. Now it's going to say the absolute value of x plus 11 is less than or equal to 4. So what we talked about before was the absolute value of x. Now we're talking about an inside value. And again, if you want to hear more about this, please go to the equation video. But if the absolute value, not of x, but x plus 11 is less than or equal to 4, that means this quantity x plus 11 has to be within 4 and negative 4. So if you want to write it as a compound inequality, it would look like this. If you want to write it as two different statements, as we're probably used to, you'd say x plus 11 is less than or equal to 4, or, I'm just saying an additional one, and x plus 11 is greater than or equal to negative 4. Both of these things have to be satisfied here, so we're going to see what x needs to be between. Because I didn't really do it last time, I'll try it this time. When I subtract 11 from here, I also have to subtract 11 from here and from here. And then you are going to be left with a compound inequality that will be your final statement here, what x is going to be between. X will be between the numbers including them, negative 15, and it appears to be, I can't do subtraction, I really can't, negative 7, I think. Is that right? I'm sorry, I'm trying to think. Yes, that's right. Okay, so x is between these two, and graphed on a number line, of course, would be between the two numbers, negative 15 and negative 7. And I still tend to just put 0 on there, just out of habit. It doesn't hurt to try putting in 0 to see if this works. So we will try that together here. Here's negative 7 if this is 0, and here's negative 15. X will be between them and including them. So close circle. I like to put the bar a little bit on top, especially if you're using a pencil and they give you a number line. or you have a number line and you don't draw it dark enough, there's x. Now, if I checked 0 in for this original inequality, it should not work. It should not be true. And I'm not going to test 0 each time. I'm doing it this last time here. All right, 0 plus 11 is 11. Absolute value of 11 minus 4 is less than or equal to 0. Absolute value of 11 is 11. 11 minus 4 is 7. Is 7 less than 0? Of course not. That is false. And that's what we expected. 0 is not a part of the solution set. The only ones that will work are these numbers here. Okay, number 2. Again, this one's actually probably easier in that sense now that you've actually done one that required use isolating the absolute value. The absolute value of x minus 5 is 2. So either either x minus 5 is greater than 2 or x minus 5 is less than negative 2. So notice, it is not about me making the negative 5 positive. I'm not making this positive. I'm saying what value I would place in there to make sure that it's going to be greater than 2 by putting in a certain value for x. So let's go ahead and figure this out. Add 5. Add 5, of course. Don't have much room. Here I will have either x is less than or equal to, it looks like 3. Oh, not equal to, I'm sorry. Just less than. Just have it. I'm sorry. X is less than 3, or x is greater than, it looks like 7. So with this graph here, of course, 0, 3, 7, open circles, x goes this way, x also goes this way. Now, if you test 0, it's actually going to be a part of that solution set right here. You'd probably have to test multiple numbers there. And we are going to have instances where we are going to test multiple numbers after the absolute value talk here. Okay, the absolute value of x plus 10 is greater than 2. Let's isolate that absolute value of x by subtracting 10 first to begin with. And now you are going to get the absolute value of x is greater than negative 8. Now, a couple things with this problem, because this one's a little bit different here. If we were looking at an equation, absolute value of x is equal to negative 8, you would automatically say no solution. And the reason is because there is no value that you can substitute, there is nothing you can take the absolute value of and get a negative number out. But I want you to remember what we're doing here. We're doing inequalities. And we're comparing to something, then we're saying that it's greater than it. Okay. So if we're comparing to something and saying that it's greater than that number, what value of x can I put in here, take the absolute value of, and be greater than negative 8? And really the answer is it can be any number. No matter what I put in here, the number will be positive, or if I put in 0, it will be 0. But no matter what I put in here, it will be positive. And any positive number is greater than negative 8, and 0 is also greater than negative 8. My solution set is all real numbers. In fact, this boundary point of negative 8 is really irrelevant. Now, this is not something where I say either it's greater than negative 8 or less than 8 or anything like that. Well, actually, technically, I could say that. That'll still use all real numbers. All real numbers. You can put anything in there and it's going to work. No matter what you put in, it'll always be greater than negative 8 or negative 1 for that matter. And if this was even 0, if this was 0 right there, as long as I don't put in 0, any number would work. So any number but 0. So there are, no matter what I put in here, that'll be good. And I know where that can trick you. So we're trying to have you avoid being tricked. Okay, now this one here, negative 7 minus the absolute value of x plus 1 is less than or equal to 0. Let's go ahead and once again get that absolute value all by itself, and that includes the negative in front of it. So absolute value, negative absolute value of x plus 1 is less than or equal to 7. Multiply or divide both sides by negative 1. Okay? Now you do that, we're going to get the absolute value of x plus 1 is greater than or equal to negative 7. Once again, you're at a scenario here where you're going to get all real numbers. To be honest, I think that when I set up this problem, I think it was supposed to end up being less than or equal to negative 7. So if you don't mind, I'm going to alter this problem in such a way so that it's actually beneficial to your cause there. Pretend like in the beginning this said greater than or equal to. So here it says greater than or equal to. So when flipped, it now says less than or equal to, because I want to talk about the opposite scenario. Now we're looking at a scenario where we're saying, okay, we take the absolute value of something, it needs to be less than negative 7 or equal to it. How do we do that? Well, we can't. It is impossible. This is a no solution case. Once again, cannot take the absolute value of anything and get a negative number as a result. And that is exactly what we need, and we can't do it. And there you go. 1, 2, 3, 4. Okay, I'm going to break away from that just for a moment. The restrictions in the domain here will work effectively a little bit later in this slideshow. I wasn't really sure where to put it, but I knew I wanted to put it before rational inequalities. So restrictions in the domain. Okay, your domain, just so you know, because I'm not defining it here, domain has to do with what values of x can you use or can't you use in an expression or in an equation. For the most part, most things that we do, your domain is all real numbers. No matter what you substitute, you will always get a value out for y. But you have cases such as these two, and I'm not saying these are the only two, but if you were doing algebra, like algebra 1 algebra, these would be the only two cases that you look at. You cannot let your denominator equal 0 because you can't divide by 0, and you cannot take the square root of a negative number. Those are two big things here, and so that's what we're talking about here. You have to really be observant whenever you're doing an equation or you're simplifying an expression that you restrict the things that x is not allowed to be. So that way, if you're solving for it or you're talking about the expression itself, you just got to say, hey, by the way, x can't be these things. Otherwise it's no good. You're just going to get some sort of error, literally a domain error. So you have to restrict it from doing that. So how do you do that? To do so, you have to work out a new equation or inequality that remedies this exact concern. So in an example where your denominator cannot equal 0, I have this expression here. We could set it equal to something, but I'm not concerned about that. Just basically, if I plugged in values for x, what values of x would not work? Here we go. What I have to do, essentially, is I have to say that my denominator cannot be 0. So I'm going to create an equation where that bottom guy, x squared minus 9x plus 18, cannot equal 0. Now that cannot equal to sign looks really funny to you, but honestly, when you're solving for x, you do it just like any other equation. You might as well say equals 0 for now, as you're practicing and testing and doing whatever, because your perception is key for this thing, and it might really affect you if you don't. This is factorable, though. This factors to x minus 6 times x minus 3 is not equal to 0, right? So the not 0 product property, I'm trying to be math funny, it's not really working. If x minus 6 was not equal to 0, or could not be x equal to 0, then x could not be equal to 6. Likewise, if x minus 3 could not be equal to 0, then x could not be equal to 3. And if you test those, 6 squared is 36, minus 9 times 6 is 54. That gives us negative 18, plus 18 is 0. See, 6 would have been an issue. If you do 3, that'd be 9 minus 27, which is negative 18, plus 18 is 0. So here are your two restrictions. X could not be 6, x could not be 3. If you do, you'll have an issue. Now, something else with this problem that I want you to see, I'm going to go ahead and simplify this a little bit. If I pull out a 3 from the top, just like dividing it out, I'm going to get x minus 3 inside. And also, if I write this in factored form, it'll be x minus 6 times x minus 3. Now, what you have is a common multiple of x minus 3 on top and bottom. So what I can actually do to this problem is take those out, and now that's 3 over x minus 6. However, that was not the original inequality. If you go and graph this, in fact, what I'm going to do with this thing is I do have a graphing calculator here. So I'm going to just go up here. I'm going to do this equation right here, 3 over x minus 6. And what you're going to get as a result is a graph. And if you haven't seen these kinds of graphs before, hang on, let's get an appropriate window. Let's go negative, oh, it's weird, 9.4 to 9.4, negative 6.2 to 6.2. And maybe this isn't a perfect window, but you'll see the effect still. So as we look at this graph here, you're going to get this curve right here, and that's going to jump up and it's going to do that right there. And there's an asymptote at x equals 6, basically. So what's happening is you can't substitute 6 into there because you get something. But anything to the left of 6, you're apparently going to get a negative number. Anything to the right, you're going to get a positive number. Now, I'm going to pull that one away for a second. I'm going to go ahead and hide that one. I'm going to go ahead and do the original equation that was above that, which was 3x minus 9. Oh, I need parentheses. Hang on. 3x minus 9 divided by x squared minus 9x plus 18. And you are going to see the same graph. It's pretty much going to be the same thing. You might not be convinced that there's anything different about it. Okay? Now we're going to take a look at that. Now the reason is because these are the same expression, right? They both represent the same thing. One's a canceled version of the other. The problem is we did take out one of our restrictions in our domain, right? So we graph this thing, and you say, hey, look, it's the same thing. But I don't know if you notice here. I'm going to go over here a little bit. Do you see that? I'm going to zoom in at 3, -1. Zoom. Let's go in closer. Let's take a closer peek. See that little hole? See that little empty space right there? That jump? If you don't believe me, I mean, I'll keep zooming in, but there's a tiny, tiny hole there. And I promise you it was not there for the other one. You can rewind the video and see. It was not there. Zoom in one more time, because I'm just having fun with it. I don't think the hole gets any larger, so you just have to convince yourself. See that little break? You see that? I see that thing. There's a little break right there. And if you're not convinced still, what I'm going to do is highlight both of these and go to the table. Okay, now the table is going to reveal it. Take a look at where x equals 6. Error. We can't divide by 0. When x equals 3, our first equation, it's fine. It gives us a solution. Second equation, error. So the thing about this is you are okay to simplify this into 3 over x minus 6. It's perfectly okay to do that. But what you have to do is you have to list restrictions. Now, one of the restrictions you still clearly see. You know that the restriction is x cannot equal 6. But what you can't see anymore that you cleared out was that x couldn't equal 3 either. So as you write this expression, you have to make sure that you still note that these things still happen because your original expression was this. So went a little bit off track, but when it comes to canceling things, remember that they still existed originally, so you have to make note of them. Just because they cleared out at one point does not mean a thing. So the setup for that thing was saying that the bottom couldn't equal 0, whatever it was, and we found out what x values were as a result. Okay, this one, if you have any sort of square root, 4th root, 6th root, 8th root, any sort of even root thing, you cannot take that even root of a negative number. So what we have to do is look at this inside value here, and we have to say this inside value cannot be negative. Now, I'm not going to make an cannot be less than or anything like that. I'll just say this must be 0 or greater than or equal to. So this still has to do with inequalities. I have to make sure that my x plus 7 value, whatever it is at least 0 or a positive number, because I can take the square root of 0 in positive numbers. So subtract 7, it'll say x is greater than or equal to -7. Because if you use the number -6, look, it's not about x being negative. If I substitute -6 for x, well, -6 plus 7 is 1, and I can take the square root of 1. So that's fine. But I can't do -8. -8 plus 7 is -1, and I can't take the square root of -1. There's not much more to say about that one. That's kind of why the square root graphs stop, though. That might be a good indication. Okay, let's start to go to some of the really, stuff's a little tougher. This is probably why you're here. We ought to solve polynomial and rational inequalities. Okay, so to start off with, and this is something that I've talked about with an equation before. If you have a solution or a set of solutions in an equation, when you're comparing the left and right side and you get x equals this and x equals that and whatever else, that means that when we substitute that value for x back into the original equation, you get the left and right statement to be the same, right, where they equal each other. However, you're also getting a number. Now, that number is actually a y value, and that y value happens to be where you're at. So let's say I had, 2x plus 4 equals x plus 9. And then you subtract x and subtract 4, and you get x equals 5. Okay, so this is the x value that I want to go to, and when I substitute 5 into either equation, I'm going to get the same number. What number? 14. 14 equals 14. So all that means is that on both of these graphs, you see where I said if both sides of the equation were graphed against y? I'm saying that if I made this y equals 2x plus 4, and I did y equals x plus 9, when you go to graph these both not only cross at 5, 14, but there's a point on the graph that's 5, 14. So they're the same at that point. That's where they're equal to each other. Okay? That's where they are equal to each other. I'm going to say that one more time. That's where they are equal to each other. In an inequality, when you compare the left and right side, what we're trying to do is satisfy the inequality. We're trying to say if the right side is greater than the left side or the left side is greater than the right side, then something's going to happen. So we're not trying to see where they're equal. We're trying to see where one's greater than the other. Now, we are going to call that point That boundary point that we're talking about where they intersect, a critical point. Okay? Critical points contain a critical number in the x-coordinate because a value left or right of it would make one expression less or greater than the other. Let's go back to that scenario I just said before. Y equals 2x plus 4 and y equals, what was it, x plus 9. If I graphed these two right here, okay, 2x plus 4 has a slope of 2 crossing at 4. Let's say it looks like this. Y equals x plus 9 has a less steep slope, and it crosses up at 9. And here's where they intersect. And this intersection point is 5, 14. Well, if I go to the left, I just pointed right. If I go to the left of 5, 14, if I do x equals 4, which one's bigger? The green one's bigger when x is 4 or less. How about on the right side? Which one's bigger? The purple one's bigger. So when you compare to the left and right of the critical number, then you actually get to see where something is true or not true. And those are the tests that we're going to do, only we're not going to do it for linear functions. No, we are going to do it for quadratic, like polynomial, mostly quadratic, and rational inequalities. But just to keep kind of going with this right here, if I was talking about that, the 2x plus 4 is greater than x plus 9. Okay, well, in this case, you'll get x is greater than 5. So any value that is 5 or greater, then, as this is the boundary value, if I go to the right, the purple one, 2x plus 4, will be bigger. That's what they're saying. If x is greater than 5, this one will be bigger. If we had a different statement, x is less than 5, the other one would be bigger. So, yeah, so there you go. Let's go ahead and start looking at the steps on how we're going to solve this. Then we're going to do 3 examples. This is for polynomial. And then we're going to do that same thing for rational. Now, they both kind of have the same steps. For rational, however, we're going to talk about the domain again. Elements not in the domain, this is actually an important point. Elements not in the domain are also critical numbers determiners. So if you find a restriction in the domain, you're going to consider that a critical number because of that asymptote stuff we were talking about. Okay, so to solve a polynomial inequality, really we just got to treat it like an equal sign. Just solve the equation. You don't have to do the equal sign thing. If you're fine with the inequality stuff, go ahead. But right now, we are just trying to find the critical numbers. So as you get one, just go ahead and find it, solve it, and you're good. Okay? You determine those things to be critical numbers. Okay? Next step. Well, they serve as critical numbers, so that's the next step. Critical numbers only satisfy the inequality if greater than or equal to or less than or equal to was originally used. So if you do greater than or less than, then the critical number is not going to help represent a true statement for your inequality. But if it's also equal to, then it will. We'll make sure to see that when we do a test. Okay, when you get a critical number, you have to test a value to the left of it and to the right of it because you need to see which sets of critical numbers satisfy your inequality. And some of this might sound really confusing without the example, so I'll make sure to go to the graphing calculator, so at least the very first example, to show you exactly why this is happening. You saw it with the last graph that I did, but you'll see why you have to do left and right for kind of almost all of them. You really want to make sure that it's always what it is that you think it's supposed to be. If it makes things easier, set your inequality equal to 0. For the most part, your equations will already be like that. Your inequalities. Now the values that you test, if they satisfy the inequality, then it's part of the solution set. And then we'll graph it. If it does not satisfy the inequality, it'll not be a part of the solution set. So I know you're already sick of the rules or the instructions. Let's go ahead and keep those instructions off to the side without the smaller bullet points. Here's an example. 3x squared plus 2x minus 5 is less than 0. So what we're looking at as a graph, let's go ahead and graph this guy here. On a graph, what we're doing is we're trying to see what values of x will it be so that when we substitute it into here, we are going to get a negative result. So what I'm going to do is I'm going to graph 3x squared plus 2x minus 5. And I have to fix my window again too. Perfect. Okay, let's see what the graph looks like. Perfect. Okay, so we see a parabola, right? Now the parabola gives us x comma y values. At the value x equals negative 2.4, the y value is somewhere up here, around 6, right? When you substitute negative 2.4, you get 6 out. Does that satisfy this inequality? No. Go a little lower. How about -2? X equals -2. Y is about 2, 2.5, whatever it is. When you substitute that in there, does it satisfy it? No. The x-intercept even? No, because you're going to get the value 0, and 0 is not less than 0. Now, I'm not certain that it's exactly at -1.8. We'll solve it ourselves and see. But if I go over here at -1, what's the y value? Well, your y value is -3.6 or something like that. I don't know what it is. Probably -4 now that I think about it. Is -4 less than 0? You betcha. So -1 satisfies this solution set. Not only that, but everything between these two x-intercepts will satisfy the solution set because I'm solving for x against y equals 0. Remember, I'm comparing this equation to this equation. Just like we did in the last set with the linear equations on those graphs, I could theoretically graph y equals 3x squared plus 2x minus 5 and y equals 0. Find their points of intersection. I don't know if that was right. Find their points of intersection right here. These are the critical points. Whatever these two things are, I want a test of x value that's to the left, in the middle, and to the right. And what's going to happen is, at least in this case, when we test to the left of our leftmost critical value, we're going to get a false statement. When we test to the right, in the middle, we're going to get a true statement. And to the right, also it's above, we're going to get a false statement. So I'm giving you the answer kind of before giving you the answer, but we still got to find out what those values are. So we still have to solve for x here. So using that graphing calculator kind of hopefully sort of helps with what it is that we're doing. Let's go ahead and actually do it now. This thing's factorable, and I'm not going to talk about the factoring stuff too much. I have to try this in my head, though. And by the way, I'm going to set it equal to it for now. I'm just going to figure out what the critical points are. This looks like -5, +1, is a -1 and +5. Okay, so this factors out to here. Zero product property says 3x plus 5 equals 0 or x minus 1 equals 0. So either x equals 1 or x equals -5/3. Okay? So here are your two critical points, -5/3 and +1. What this means, once again, is on your graph. Do I still have it up? Yes. On your graph right here, -5/3 is around -1.6, -1.66666. On your graph, we want to test a value to the left of -5/3, somewhere over here. Maybe I'll try -10. Doesn't matter. Any number. Any of these will still have the same thing, something way up here, right? We're going to get a positive number. It will make a false statement, and we'll say that, okay, that's not a part of our solution set. Now, -5/3 is also not a part of our solution set because this inequality was a less than inequality. It wasn't a less than or equal to. If it was less than or equal to, it would also be included on our graph. When we test a value in the middle, right here, I'm going to test the number 0. It's pretty easy to do. I will get a true statement, and then I'm going to test a number to the right of 1, maybe just 2, and I'll get a false statement. So let's try it. Explaining it through the answer sometimes helps you work out the rest of them. So let's test. So we know our critical values there. So let's test some numbers. Let's test. I'll do the work inside here. Well, I'll try -5. Whoops. -5 and 0 and 2. -5 is to the left of this critical point. 0 is in between these two critical points. And 2 is to the right of this critical point. So let's see what we do. We'll get, what was the original one? So here's what we're going to do. Now we're going to test it against this inequality. 3x squared plus 2x minus 5 is less than 0. And where I said if it makes things easier, I'm going back. If it makes things easier, you may modify it so it's set against 0. The reason is because your only test is not, all you're testing is your number negative or positive, right? If it's negative, it'll be true. If it's positive, it'll be false. That's it. So that's why it's sometimes easy to just test against 0. 3 times -5 squared plus 2 times -5, and I guarantee you I won't be doing this each time. -5 squared is 25. 3 times 25 is 75. Minus 10 is 65. Minus 5 is 60. 60 is positive. This is false. That is not less than 0. 0, plug it in. 0 plus 0 minus 5 is -5. Is -5 less than 0? It's negative. And 2 squared 4 times 3 is 12, plus 4 is 16, minus 5 is 11. 11 is positive. This will be false as well. So what it comes down to now is the graph. Your x values that you can choose can be between -5/3 and 1, and it cannot include those two. Those are the ones that will give you the true statement for this. So when I substitute any numbers between -5/3 and 1, I will get a negative number, and that's exactly what I was looking for here. Okay? So now let's graph it. And you may say, oh, that was kind of hard and such. Oh, we'll do a couple more examples. I'm not going to do a lot of the graphs alongside it, right? The graphing calculator things. I'll find the critical points and test them again. Maybe when you hear it more and more, it'll kind of come more naturally. Here's 0. Here's -5/3. Here's 1. Here's x. Cannot be these, but it can be these. All right. There's your graph. There's your solution set. Let's do it again. X squared plus x is greater than or equal to 20. Now, if you graph these specifically at this point, I just said I wouldn't graph. I mean, I won't do it with the graphing calculator. If I graph these two things specifically, and I don't know what x squared plus x looks like, at least not off the top of my head. I'm not too concerned about it. But I know here's y equals 20, way up here. And then here's some parabola, x squared plus x. I do know it crosses at 0. But let's say this is your graph right here. Okay, well, these are your critical points. All right, but what I'm going to do is I'm going to subtract 20 from both sides. And I'll get x squared plus x minus 20 is greater than or equal to 0. What's going to happen essentially is you're now comparing this equation with y equals 0. What do these two graphs look like? Same thing, but shifted down 20 units. Critical points will still be the same. Okay, so no matter whether I do it as the original inequality or anything or equal to 0 or whatever, they're still going to have the same exact critical points. It's just shifted down 20, right? We subtract 20. So that's basically what it comes down to. So here, let's go ahead and subtract. So we did do that. So now I'm going to go ahead and solve for this thing. Let's set it equal to 20, or to 0, plus x minus 20 is equal to 0. As I factor, that'll be x plus 5 times x minus 4 is equal to 0. So x plus 5 equals 0. This kind of stuff takes a while. So x can be negative. Well, not it can be. These are my critical points. Critical point -5 and a critical point of 4. So once again, you did see a parabola, right? We just talked about what kind of graph this is. We know it's an upward-facing graph. We know it's a parabolic one. It's quadratic. It's doing something here. What's crossing there and there. And once again, if you know what your graph looks like, then you have no problem. But if we were doing, let's say, a cubic function or something, and you truly don't know what's happening, then maybe you're not sure how to test it. Now, remember, this is the test we're going to do. We need to test numbers to the left of -5, to the right of 4, and in between -5 and 4. We got to see which ones will give us numbers that are greater than 0, or in other words, positive numbers. This is why setting it equal to 0 once again is good, because I kind of already know my answer. And maybe you can too. Why don't you take a guess before I say it out loud? I'll give you 5 seconds. You got it? Okay, so if I graph something, if I plot something to the left of -5, it looks like I'm going to get positive numbers. To the right of 4, it looks like I'm going to get positive numbers. In between them, I'm going to get negative numbers. On them, I'm going to get 0. The only ones that will work are less than -5 and greater than 4. But don't take my word for it. Let's try it ourselves. Let's check x and y. We have to choose our own points. We're not going to choose -5 and 4. Those, we know what we're going to get out of that, 0. Let's try -10. I'm going to do 0 again. Always an easy one. Let's do 10. Sound fair? We're testing this against, I take that back. This was greater than or equal to. These do work. 0 does work on this. So see, this is why we really have to do this in math. Now these, -5 and 4 will be a part of your solution set. There's no reason to test it. We know we're going to get 0 as an answer. We found our zeros. We still have to test these ones. -10 squared is 100, minus 10 is 90, minus 20 is 70. 70 is greater than or equal to 0. This is true. 0 squared is 0, plus 0 is 0, minus 20 is -20. -20 is less than 0. That is false. And 10 squared is 100, plus 10 is 110, minus 20 is 90. This is greater than 0. It is also true. So your solution set, x can be less than or equal to -5, or, the word or is very important here, x can be greater than or equal to 4. So as we graph it, now there's no reason to test 0 because we just did it. Here's -5, here's 0, here's 4, here is x, including that value, and including that value. Awesome. So hopefully you're getting the gist of it a little bit. You're finding your zeros, you're testing against 0 based on the inequality that's stated, and you're trying to see which ones will give you which ones will satisfy the inequality. One more, -x squared minus 6x minus 9 is greater than 0. And if you're like me, you hate negatives with your leading coefficient. So what I'm going to do is I'm going to multiply both sides by -1. But remember, if I do that, I flip my inequality. X squared plus 6x plus 9 is less than 0. Okay, you might say like, oh, this is an easier problem than the last one. Maybe, I don't know. But this is x plus 3 times x plus 3. I'm going to set it equal to 0 for now, which is x plus 3 quantity squared. So you can say x plus 3 is 0, or x is -3. So here's the critical point. There's only one of them this time. Now, how come there's only one critical point here with this quadratic? In this case, your vertex is actually on the x-axis. So whatever you test on the left and the right actually ideally should be giving you the same thing, if that makes sense. Now, what was the original thing? Greater than? Oh, less than now. You can do the original one. I'm going to do this one for now. You can just do the one that you did when you modified the equation before you change it into an equal sign. So I'm going to do this one, x squared plus 6x plus 9. So I'm going to test x squared plus 6x plus 9 with a number that is to the left of -3 and to the right of -3. So let's try -5 and let's try 0. Oh, and this needs to be what? This needs to be less than 0. So if it is greater than 0, it's false. If it's less than 0, it's true. It won't become 0. The only 0 is -3. Okay, here we go. -5 squared is 25 minus 30 is -5 plus 9 is 4. That is greater than 0. That is a positive number. That is false. 0 plus 9 is 9. That is greater than 0. That is false. -3 gives you 0. I'm just going to put it here just to remind you. -3 gives you 0. 0 is not less than 0 either. That is false. There is no point anywhere. There's no x value that I can substitute for any of this or this, that will ever give me a negative number. Not that all of these do this, just in particular this one. But once again, why? It's because the graph looks like, whoops, or the new graph that I made, the modified one, has a vertex at -3. Therefore, it's just doing this. You know what I mean. It's going down to -3 and coming back up. It's never hitting negative territory, ever. There's no value that will give you 0. So all of these are false. So how do you graph it? You don't. You say no solution. That's it. Okay, let's go to rational inequalities. Now, there's not much different from here. The only big difference, because we're still going to be testing some values and stuff. Maybe it'll be harder because you have fractions. But this is really why you want to test against 0, because all you want to check is positive and negative, right? But anyway, the big difference is there's a new number 1. We have to figure out what our restrictions are beforehand, because if we cancel anything out, or if we're not paying attention to our original inequality, then we will be possibly using restrictions that can never be a part of the solution set, right? X cannot be anything that will make you divide by 0. So these will be critical numbers, okay? The rest is the same as you saw with the quadratic stuff. So if you got familiar with it, let's go ahead and do it again. Let's jump straight into the examples and see if any of this works out. Okay, 1 over x minus 4 is less than 0. Now, for this particular problem, what are the restrictions in your domain? Well, this particular domain just has the value x. Your domain cannot, your denominator cannot be 0, and x is your denominator, so x can't be 0. And that's your restriction. So 0 is one of your critical points. Let's make sure we remember that. Critical numbers. Sorry, not point, numbers. Critical numbers, 0, comma, whatever else we get. Now what we have to do is we have to solve for x in this equation. When we solve for x, that'll also become another critical point. Now remember what the original inequality was. Let's rewrite this. 1 over x minus 4 is equal to 0. I think the easiest way to solve this problem is if I add 4 to both sides. You get 1 over x equals 4. Multiply both sides by x, boom, 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 gone. 1 equals 4x, divide by 4, x equals 1/4. If you're really good at some of the stuff, you kind of know the 4 and the x switch places. But there we go. 1/4 is another critical point, because if x equaled it, well, then it would also kind of be false, at least for this point. But anyway, to the left of it and to the right of it are numbers that we have to test. So here we go. We have to test to the left of 0, in between 0 and 1/4. Ooh, that doesn't leave us with much room. And to the right of 1/4. And then after that, I'm going to go ahead and look at the graphing calculator for this graph. The graph, by the way, is y equals 1 over x minus 4. You're testing that against y equals 0, remember? This is just the x-axis. And you're going to see exactly why this thing is what it is, what we're testing. We're going to test and see a number to the left of 0. Let's try -1. We also know that'll give us a good-looking number here. We're going to test a number between 0 and 1/4. How about 1/8? And a number to the right of it. How about 1? Okay, they don't have to be far. They can be big and extreme, but small ones do work too. And let's figure out what the y values are as a result. 1 over, and we're using this, 1 over x minus 4 is less than 0. Now this was already set equal to 0, or this 0 was on the other side. So I'm good right here. 1 over -1 is -1. 1 minus 4 is -5. -5 is less than 0. This statement is true. By the way, off the top of my head, I'm not thinking about what this graph looks like. I wouldn't know, and I wouldn't know to tell you what's true or false beforehand. 1/8. Okay, 1 over 1/8 is 1 times 8 over 1. When dividing by a fraction, you multiply by its reciprocal. So 1 over 1/8 is 8. 8 minus 4 is 4. 4 is not less than 0. This one is false. So anywhere between 0 and 1/4, also including 0 and 1/4, by the way, will be false. 1 over 1 is 1. 1 minus 4 is -3. -3 is less than 0. That is true. So when we graph, and I'm not talking about graphing the inequality. I'm not talking about graphing the function. I'm talking about graphing the number line. When we graph on the number line, our solution set is that x can be less than 0, or x can be greater than, 1/4. So when I graph this one, check this out. 0 is actually a boundary point this time. There's 0. Here's 1/4. Anything between them is false. On them is false. Because remember, less than right there. So these critical points there, boom, x could be anything greater than it, that, and less than that. And what will happen, remember what we're expecting for our graph. If I substitute a value less than 0 or greater than 1/4, I am going to get a negative number. That's what I expect. I expect my y value to be less than 0, meaning on my inverse function graph, I expect it to go underneath the x-axis. Underneath the x-axis. Let's go ahead and graph y equals 1/4 x. Come here. Y equals 1 over x minus 4. Let's do that. Boom, boom, boom. 1 over x minus 4. So what does the graph look like? Once again, the graph should look like it's going to look like something weird because it's an inverse function. But when it's less than 0, it's going to be a negative. It's going to be in the negative y stuff, so underneath the x-axis. When it's between 0 and 1/4, it's going to be above the x-axis. When it's going to be 0 or 1/4, it's going to be on the x-axis. And when it's going to be greater than 1/4, it's going to be below the x-axis again. Here we go. All right, so when it is less than 0, it is below the x-axis. When it's between 0 and 1/4, I'll take a look at that in a second. When it's greater than 1/4, where is 1/4? Okay, 1/4 is around here. When it's greater than 1/4, it goes below the x-axis as well. How about between? Let's go and zoom in on this thing. Zoom in a lot. So here's 1/4 right here, where I'm blinking right there. If I go to the left of it, between 0 and 1/4, where's my function? It is above the x-axis, so that's the positive values, right? The negative values are on the other side right there. Once it hits 1/4, it's 0. Once x goes greater than 1/4, y goes less than 0. That's what we're looking for. Here are our critical numbers. Remember where we got 0? It was a restriction in the domain, so we had to get that one first. Okay. I don't know if I plan on graphing any other ones after this like that, but I will go to the last two examples. Okay, x plus 12 over x plus 2 minus 3 is greater than or equal to 0. First things first. Predetermine any possible restrictions to the domain. This cannot be 0. Therefore, x cannot be -2. This is one of your critical points. Critical numbers, critical number. Critical number, -2, comma. What else is there? Let's find out. Okay, move that out of the way. Let's go ahead, kind of same thing as last time. Let's set this equal instead. Let's add 3 over. I think that's just going to be easiest to solve for x here, instead of getting a common denominator. So equals 3. Multiply both sides by x plus 2. Right here. Boom. And you'll get x plus 12 equals 3x plus 6. Subtract this x over. Subtract this 6 over. 2x equals 6. So x equals 3. Okay, here's another critical number, 3, right there. So we've solved for x. We found a restriction in the domain. We are going to test to the left of -2, to the right of 3, and in between the numbers -2 and 3. And once again, I'm kind of uncertain what this graph looks like. So anything will be of complete shock to me, what I end up getting here. I will not show the graph in the end. I hope that you trust that what we're doing is making sense with regard to it. So to the left of -2, how about -5? Between -2 and 3, hey, 0. Remember, we can use 0. We won't have a restriction in the domain. And greater than 3, how about 5? You don't have to get, whatever. Now, what I'm going to do is I'm still going to use my original inequality because this one was good. Because what we're going to end up happening a lot of times is we're going to have a lot of fractions. And it's not that I'm going to be very curious as to what the fraction is. I just need to know whether it's positive or negative. So once again, we are testing it against this whole inequality right here. The fact they made it equal to 0, or that I did, I don't know who did it, I forget. The fact that we made it equal to compared to 0 is good. You just have to test positive versus negative. Now, keep in mind, the critical numbers will be a part of your solution set because the greater than or equal to. Okay? But when we test this, if it's positive, it's true. If it's negative, it's false. -5. -5 plus 12 is 7. 7 over -5 plus 2 is -3. 7 over -3 is a negative number, -3. A negative number minus another number will be a negative number. I don't really care what this number is. I'm not trying to calculate the whole thing. I know it's negative. Negative is not greater than or equal to 0. Whatever this number is, it's false. Okay? If you truly want to know, it's -16 over 3. -16 over 3 is false. I guess there's no reason in not writing that. But I am once again saying that that's a good reason why you want to test it against 0. Okay, let's test 0. 0 plus 12 is 12. 0 plus 2 is 2. 12 over 2 is 6. 6 minus 3 is 3. 3 is greater than 0. This is true. Let's test 5. 5 plus 12 is 17. 5 plus 2 is 7. So 17 over 7 minus 3. This might be one that you have to be very careful of. 17 over 7 is a little more than 2. It's 2 and 3/7, right? 2 and 3/7 minus 3. Okay, well that's going to be a negative number. That's -4/7. -4/7 is less than 0, so it is false. So, which values will work? X can be between -2 and 3, the critical points, including -2 and 3. All right, let's go ahead and graph it. Hopefully, after you're getting a lot of these problems here, you're really understanding what it is we're doing. And I could, you feel free to go to your graphing calculator and graph this, meaning y equals this. Feel free to graph that. You can graph it against y equals 0. That's the x-axis. If it's greater, if any parts that are positive in the y area will be true. and they will be between here, by the way. Anything that's to the right and to the left will be false because they'll be negative. Last one, and then that's it. Looks like we're testing all of these against 0. Okay, first things first. Domain x minus 2 cannot equal 0, so x cannot equal 2. There's a critical number. Critical number of 2. Let's solve the rest. Multiply both sides by x minus 2. Hang on, let me set this equal to 0. 15 over x minus 2 equals 0. If you multiply both sides by x minus 2, okay, well, it goes away here. That's why it's important to get the domain restriction first. You multiply 0 by x minus 2, you're going to get 0. It's still 0. So you have 3x plus 15 equals 0. 3x equals negative 15, so x equals negative 5. This is another critical number. Okay, so with our critical numbers here, we are going to go ahead and test to the left of negative 5, in between negative 5 and 2, and to the right of 2. With what? With this original inequality. 3x plus 15 over x minus 2 is less than or equal to 0. Okay, so x, y. Let's go ahead and choose some values for x. To the left of negative 5, negative 10. Between negative 5 and 2, why not? 0. And greater than 2, how about 5? And once again, you are only checking to see if the number is positive or negative. We know it can't be 0. We know these numbers give us 0. Positive or negative is it. Here we go. Negative 30, substituting negative 10. 3 times negative 10 is negative 30, plus 15 is negative 15. Negative 10 minus 2 is negative 12. Negative 15 over negative 12 is positive, and we can reduce that. 5 over 4, I think. 5 over 4 is not less than or equal to 0, so this is false. Okay, 0. 3 times 0 is 0 plus 15 is, I was going to say 0, is 15 over 0 minus 2. That's negative 15 over 2. So negative 15 over 2 is a negative number that will be true because it's less than 0. Finally, to the right of 2, 5. 3 times 5 is 15, plus 15 is 30. 5 minus 2 is 3. Oh, that was good. 30 over 3 is 10. 10 is not less than 0. That is false. So, x may be between negative 5 and 2, right? Including negative 5 and 2. And let's go ahead and graph that last one. And this will be it. So I sure hope that, through these scenarios, you're really getting the gist of it. Now, you might see some other ones. You might see some cubic functions, whatever else. And you can look at them in your graphing calculator, but the purpose remains the same. You first have to solve for x. Figure out what your critical points are. Be very, very, very wary about the domain stuff before you do any cancellation, because you can tell when we do some cancellation. Do some testing points. Test it against 0. Positive, negatives. Perfect for that. And that's it. So what was covered in this section? We saw some properties of inequalities. We saw things like you want to have x on the left. You want to read it like that. Multiply both sides by negative something. You flip the inequality. Yeah, I mean, that was the big stuff we were talking about. How to solve for them. How to use properties of inequalities, solve linear inequalities was there. How to solve using absolute values, right? We talked about within and outside of. Domain from unwanted solutions, and I really hit on that with the rational functions there, the rational inequalities. How to solve polynomial inequalities and rational inequalities. They really do have the same kind of idea. You have to do a lot of tests. If you have a graphing calculator, I think you're kind of good to go, as long as you understand what's being talked about there, but you want to test it against 0. That's going to be the easiest thing for you to be able to do there. And I am out. Fiend!